So let's talk about the length of curves. Recall that if we are given a motion that looks like this, okay? So we've dealt with something that looks like the motion that you have here. If you're starting from this initial position and you move, okay? Suppose we want not to get the position, but the distance traveled. So you see the blue trace that's being left behind, okay? If you want to get the length of that blue, okay? If you take that and you imagine that it's like a string that you're attaching it to this slinky looking object, right? How long is that going to be? Well, that's called the arc length. That's called the arc length of the curve. And let's talk about how we will find it. So we've encountered, measuring lengths in many different things in our geometry class. But when you have curves that look like this, they bend, then we're going to have some kind of extra tricks in order to find the lengths of these. Okay? You can't just use some kind of trigonometric identity or things dealing with perimeter that you might have. We have to find some other trick. Well, notice that if you zoom in on a very small piece of this curve, okay, so this is what we get when we zoom in, well, then the curve looks approximately straight. And the more you zoom in, the more straight it is. So zoom in enough until this is fairly straight, and you then have that the length of the curve in just that very tiny segment is equal to the square root of delta x squared plus delta y squared, where delta y is the rise and delta x is the run. Okay? Now, we want a way, so you might say, okay, that's just one tiny segment. We want a way to be able to look at all of the different segments along that curve. What we're going to do in order to obtain that is to say, put a bird over here or an ant and let it walk, okay? So that its position vector is given by this purple vector there, okay? And we're going to use our clock for time. So we're going to track the motion along this curve using time. And what we could do then is ask this ant that's moving along the curve how fast it's going at different times. Okay, and from knowing how fast it's going and how long it takes to go over a small segment, we can get the total length of this. Do you see the strategy, how we're kind of doing it? So if we take the delta t that it takes to move across that small segment there, and we divide by it, okay? Then we could simplify this delta s over delta t. Delta s over delta t is the speed. Okay, it's the change in length, the actual length, over the change in time. And we could stick this delta t into the square root by squaring it and then inserting it into the square root and distributing to get this object here. So indeed, we do end up getting the speed. Now, we want to be very accurate, so the time chunks that we're going to use are going to be the limit as delta t goes to 0, and once we take the limit as delta t goes to 0, we get a derivative, okay? And again, if you want the length now, you just ask the ant at some time. Say the ant is over here at that time. You ask it, how fast is it going, okay? How fast are you going? That's going to be given by the speed. Okay, that's going to give you the speed in the x direction, speed in the y direction, and you multiply its speed by the time to get the small length that it travels in that very small chunk of time. Okay, so simplifying this expression, we could just write dx dt as x prime and y prime, and we could also write this here as just the magnitude of the velocity or the speed, okay? So the length, the small length along in a small delta t is given by the speed times the delta t. And what do you do when you want all of the length, so the length for the whole thing? Well, you add up all these small pieces, and you add up all these small pieces by taking the integral. Okay, taking the integral gives us the total length, and we do this again. So hopefully now you see why we needed that time parameter. It's because we needed a way to move along this this curve. Okay, and as we move along this curve, we take very small ds's, add them together, and this here is the integral. So this, what you're seeing here, is the speed. And you know, this was in 2 dimensions up here, and now we just added the third. It's a straightforward way to add it. It's a, you know, you just get an extra dz dt. And this represents the speed. This is the small amount of time. And the smaller we get, the better, right? Since the speed could possibly change as we move along here. So we want very small time chunks. So this represents the small distance that you travel in a small time. And then this integral is to add up all those small distances together to get that total length. Something important to notice is that we want the length from t equals a to t equals b. Okay, so this is the length that we would travel across if we started the time at t equals a and ended at time t equals b, which corresponds, by the way, to beginning at position RA. So this could possibly be RA, for example, that vector there, and say we wanted to end up here, that would be RB. Okay, the position at time t equals b and the position at time t equals a. And what's the distance traveled as you move from RA to RB along this curve? Well, it will be this integral here from a to b of the speed. And I should point out, and this becomes important in a later chapter, that getting this r of t, this is called the parameterization. Okay, to describe this curve as you move along in time, or you know, some other parameter. Here I'm just using time as a sort of analogy, an intuitive analogy, but you could use any parameter to parameterize this curve, but you still need this vector function that travels along the curve. That here is what's called the parameterization of a curve. So let's apply that formula. In fact, let's use that example that we saw when we first started this video of the motion along that spiral. Okay, so we had a position vector that looked like this. Okay, and we want to find the length of the path from t equals 0 to t equals 10. Well, one ingredient is the speed here, right? Okay, one ingredient is the speed. So we're going to find the speed. We already have our parameterization. That's already given to us. In later chapters, we'll even have to get that. But for now, we already have that. So that's easy. So let's get the speed. Well, to get the speed, what is the speed? It's the magnitude of the derivative. So magnitude of the velocity. So we're going to take the derivative. Okay. When you take the derivative of this is what gives you the velocity right there. And we don't want the velocity, we want the magnitude of the velocity to get the speed. So we just take the magnitude, okay, simplify the magnitude, and it's a number. So as we're moving along the spiral, the velocity changes, but the speed actually ends up staying constant. And now let's apply the length formula. So we're going to put the ingredients together, making sure we get the correct bounds. We have our speed here, which just turned out to be the constant 269. And we started at t equals 0 and are going to t equals 10. So that's where the a and b are being filled. And it's just a straightforward integral at that point. So the length of that spiral that you saw is 2,690.